Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we discussed emergency operating modes of autotransformers, short circuits, overvoltages, and protection methods. Today we are completing this series and will talk about the tertiary winding. We will explain its role in the circuit, its functions, and the conditions when it can be omitted. We will also examine how designers make decisions on structural optimization, balancing cost, weight, and reliability. A tertiary winding is an additional winding, usually connected in a delta. It does not participate in the main power transfer between high voltage and low voltage windings. It provides closing of zero-sequence currents, stabilization of the neutral under unbalanced load, suppression of the third harmonic, and its multiples supply to local networks for own needs or nearby loads. Its rated power may range from 10 to 35% of the transformer's total power, depending on its purpose. Physical role of the tertiary winding. Without the tertiary winding, during asymmetry or single-phase loading, magnetic balance is disturbed, unwanted currents appear inside the tank, and structural elements become magnetized. The tertiary winding closes the circulating current within itself and does not let it enter the tank. This reduces energy losses, increases stability, and lowers voltage distortion. Loss calculations also consider the contribution of third harmonic magnetizing current, and its compensation is most effective when the tertiary winding is connected in a closed delta. The tertiary winding closes the third harmonic currents that appear during no-load operation with grounded neutral. Without it, distortions grow, along with radio interference and vibrations. In some cases, harmonics may even cause resonance in cable lines or reactors. This effect is especially critical in urban networks and communication facilities where harmonics can influence the accuracy of equipment and the stability of control systems. Reduction of zero-sequence impedance. In the case of a single-phase short circuit, the impedance of the zero-sequence path is a key parameter. With a tertiary winding, this impedance is 3 to 5 times lower. That improves stability during short circuits and reduces overvoltages on healthy phases. For example, without a closed delta, the voltage on the opposite phase may exceed 115% of the nominal value. This can trigger unwanted protection or even damage the insulation. Can we omit the tertiary winding? In some cases, it can be left out if the network is isolated or does not require grounding, if calculations confirm that voltage distortion and zero-sequence currents remain within acceptable limits, if special measures are used, such as shields, limiters, or compensators. However, removing the tertiary winding requires detailed circuit analysis and operating models. In international practice, for example in the US, omitting the tertiary winding is more acceptable when fast response breakers and accurate digital protection systems are in use. Structural implementation. Possible design variants include inside the tank, placed on the lower yoke as a separate section between the high voltage and low voltage windings as a single layer winding if its power is relatively small. The location of the tertiary winding affects cooling efficiency and the mechanical strength of the transformer. For a tertiary winding rated at 1/3 of the main power, transformer cost increases by about 10%. The main goal is to minimize the total cost. The calculation is shown on screen as total cost equals cost of manufacturing, plus cost of capitalized losses, plus cost of operation, plus cost of repair. The engineer compares no load and load losses, mass and cost of copper and steel, dimensions important for transportation and installation, environmental conditions such as temperature, humidity, and accessibility, standards for service and repairability. In 500 kilovolt transformers and above, part of the tertiary winding may be made of aluminum, if overload capacity is not critical. This reduces overall weight and price by 5 to 7%. Examples of optimization replacing the steel with thinner material. Losses decrease by 15%, cost increases by 5%, and mass increases by 2%. Increasing the cross-section of the winding, load losses decrease by 20%, mass increases by 10%, and price increases by 7%. Optimizing the location of cooling channels, heating losses decrease by 10 to 15%, and service life increases by about 8 years. Optimization is always about finding the balance. The calculation is shown on screen as coefficient equals change in capitalization divided by change in cost. If this coefficient is more than 1, the investment pays back within service life. Practical decision. For example, a transformer rated at 160 megavolt amperes with tertiary winding, stable operation under unbalanced load, controlled short-circuit currents, and minimal distortion. Without tertiary winding, tank losses grow, harmonics increase, current waveform is distorted, and fault clearing time gets longer. A balanced calculation shows that the tertiary winding pays back in 5 to 6 years of operation at an average load of 70% and energy price of 4 rubles per kilowatt hour. Practical analogy, imagine a 3-legged swing where one leg loses its stability. Without the tertiary support, the whole structure shakes. With the tertiary support, the system is balanced. Another example, an air conditioning system without a filter, air is supplied but dust keeps accumulating. Here the filter is the tertiary winding, stabilizing the quality. Practical task, calculate the zero sequence impedance with and without the tertiary winding under single-phase short circuit. Determine how this affects the voltage of the healthy phases. Analyze at what level of short circuit current the tertiary winding becomes mandatory. Calculate the payback period of the tertiary winding for a given load and energy tariff. Today we have learned why the tertiary winding is needed and its key functions, when it may be omitted and what can compensate for it, how engineers find balance between losses, weight, and cost, and why proper optimization is an investment in reliability and not redundancy. In the next series, we will explore impulse voltages and how to calculate the initial voltage distribution. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.